Hello everyone, welcome again in Eng-Man YouTube channel. So we will continue our learning on CO2 sequestration modeling. It's in saline aquifer and we will perform it using CMG software. And in previous video, we have constructed a model with structural hysteresis and also solubility trapping. We already did the modification or the modeling, the fluid modeling using wind probe. And then we also have run the simulation on the gem. So in this video, we will visualize the results. So I already opened my results. And of course, we will take this .sr3. Click on open. There you go. So let's go to this reservoir model. And you can see the 3D view as usual, but let's go first to 2D view like this. Okay, and then go to display. And what do we want to look at? Maybe first we can go to, as usual, gas saturation. Okay, play. All right. Now you see the red area, now it's very short. And we still have the yellow area, showing that the CO2 is trapped by hysteresis trapping and also added by the solubility trapping. Okay, it's very interesting. And because of the solubility trapping now we have even stronger trapping, which will restrict the movement of CO2, which will restrict the propagation of the CO2. That's why you have CO2 that is shorter on the top of the aquifer, on the top of the storage. So this is how the gas saturation looks like. And of course, we can also check as usual again. Yeah, right. It's very different from structural trapping. It's very different from structural plus hysteresis trapping only. Go back and play. Right. Short, and you see more and more CO2 trapped from the bottom up to the top. Okay, it's very interesting. And we also now is very interested to look at the water mole fraction of CO2. So this is the CO2 dissolved in the water. And we want to know the mole fraction of the CO2 within the water. So it's wise to go back and yeah, let's go to water mole fraction. Starting from red color. All right, you can see there. You see now, interesting. Okay, we can also adjust color scale editor, and let's say I want to make it maximum to be like this. Okay. Wow. Right. So now mole fraction, more and more CO2 dissolve in the water in the brine, and you see the shape, the profile is like this, right? So at the bottom it is sort of covers more area than what we have on the top. You see, because now CO2 being dissolved in the water becomes actually heavier than water without dissolved CO2. Okay, so if the CO2 is dissolved by or if it is dissolved into the brine, the brine will be heavier, so it will of course go down because of gravity. Okay, we can also, yeah, again, so we can also check the same thing, water mass density. You see, right? But maybe we can adjust the scale. Hopefully we can see even more clear difference. And what about like this? You see there. Okay, and also like this. Now, all right. The density, the blue density is heavier, is higher than the red density. Okay, so now water with dissolved CO2 will be heavier than all other brine without CO2. So now water containing CO2 will sink to the bottom of the aquifer because of gravity, which is good. So because now our CO2, which is greenhouse gas, now the CO2 is trapped, being dissolved in the water, and it sinks. It goes to the bottom of the aquifer, making the escape of CO2 into the atmosphere much more difficult. Okay, so being accumulated at the bottom will increase the safety, will increase the permanence of the CO2 being trapped or contained in the storage. So that's the idea. It's very, very, very interesting. And we are also interested in comparing, this result with structural trapping only and with structural plus hysteresis trapping. And I'm not sure whether our model is, you know, infinite or not, but maybe it's not infinite in infinite aquifer. So I will take from case 2A. Let's rename it case 2A. Okay. And I will take the case from that. Now we have structural trapping only, structural plus hysteresis only, and structural plus hysteresis plus solubility trapping. So to compare the three, I will first take this structural and let's put it on the bottom, on the dashboard, I mean. Okay. And now the 2A, structural plus hysteresis only, drop it there. And lastly, 3A, structural plus hysteresis plus solubility. All right. And let's check the display. 2D view. This also 2D view. And lastly, 2D view. Okay, make some adjustment in if you want. Can we do that? Okay. And there. Okay. Yeah, sometimes it's a little bit difficult, but yeah. Okay, I hope you get that. Squeeze it and let's expand it a little bit. Okay, so now let's change everything in gas saturation first. Gas saturation. Okay, so now let's just play. You see on the left, we have structural trapping only. Okay, that's why, because now the trapping is the weakest, it can propagate far away from the well. Okay, very few CO2 being trapped at this section. Okay, almost all CO2 is trapped by the structural boundary at the top. And now we have also on the right, oh, I cannot do that. And maybe I can, oh, I want to touch this and move to the right. And let's expand it. Okay, beautiful. Okay, make it smaller. Okay. And on at the middle, we have structural plus hysteresis only without solubility. And as you can see, now we have more yellow area because we have more trapping by the hysteresis effect. And the propagation of CO2 at the top becomes, shorter because now we have stronger trapping that will restrict the movement or the propagation or the migration of CO2. Okay, but on the right, we have now more contribution from solubility trapping and the propagation of the CO2 even shorter, but we have more yellow area because now more and more CO2 is trapped. Okay, CO2 is trapped by not only hysteresis but also by solubility trapping. And we can also check as usual this. They are different, completely different, right? Especially structural trapping only. Let's show it again. Okay. All right. Okay. Beautiful. Very, very, very different. Okay. Now the hysteresis dynamic trap gas saturation is 0.05 here. And but we have greater saturation there. Greater saturation there. Okay. And of course, we can also check water mole fraction. Only the solubility trapping has it. Okay, because we only have the trapping of CO2 by dissolving it into the water only in solubility trapping case. Okay. Structural trapping case and structural plus hysteresis trapping case do not dissolve the water. And of course, we can also change it to mass density, water mass density, and the same result with water CO2 mole fraction will occur. Okay. And you see here the mass density is 1006. Here also 1006. But now we have greater than 1018 because of now CO2 being dissolved into the water, making the brine heavier and more dense. Okay, so you get that. It's very interesting. Now we can also check the time series plot as usual. Okay, so now we go to time series and special history. Now let's see the 3A and then special history. Now let's see the CO2 supercritical first. Add to new plot. Okay, so now CO2 supercritical, the profile decreases, shows decreasing trend. Why? Because as we move across time, as we move forward across time, more and more CO2 now will be dissolved into the water. Okay, so that's why we'll have less supercritical CO2. Let's plot CO2 trap. Okay, let's plot CO2 mineral. Of course, it will be 0. CO2 liquid, 0. CO2 gas, 0. CO2 ions, 0. CO2 dissolve. You have value there. Okay, so now let's delete curve. Sorry, should be this. Okay, lastly. Okay, let's plot CO2 dissolve again. Now you have CO2 being dissolved. This explains why you have decreasing CO2 supercritical, because more and more CO2 will be trapped being dissolved into the brine. Okay, and of course we can compare CO2 supercritical. I want to compare CO2 supercritical first from 3 cases. Like this, from structural trapping, it is higher, and structural plus hysteresis trapping, it has the same value with CO2 trapped by structural trapping only. Okay, you have less CO2 supercritical because more and more CO2 being dissolved into the water, which makes now CO2 no longer in free state, supercritical free state. It is now another entity. It's no longer actually pure free CO2 because CO2 dissolved into the brine. Okay. Okay, and let's delete curve again. Delete curve. Delete curve. Let's compare 3A special history 3A. Now CO2 trap. It's like this. Compare it to structural only. Okay. And structural plus hysteresis. Okay. So now we can understand what is CO2 trap. CO2 trap, actually CO2 trap because of hysteresis trapping, right? CO2 trap as CO2 residual CO2 being trapped in the pores by the hysteresis effect, by the, critical gas saturation effect. You have the least CO2 trap because in structural trapping only, because you see we have low critical gas saturation, which makes more and more CO2 being escaped from the pores as it propagates farther and farther from the well. As we increase the hysteresis effect, now critical gas saturation or residual gas saturation becomes higher. It means more and more CO2 being trapped in the pore spaces because of capillary effect or hysteresis effect. Okay? Actually, hysteresis plus solubility supposed to have, the same amount of CO2 trap. But why we have less CO2 trap here? Yes, again, because now we have CO2 moves into the water. Yes, first CO2 trap in the pore spaces, but it will not stay there as being trapped in the pore spaces. It will be dissolved into the water instead of staying on the pore spaces as residual CO2. So that's why you have less CO2 trap in the case of solubility trapping than in the case of hysteresis without solubility trapping. Okay, so it's, very, very interesting. Maybe lastly, profile. What can we see here? Let's see. Well, 3A, CO2 injector, gas mass density. Oh, now we have to move across time. Let's see at the end. Okay, so it's like this. Okay. All right. The horizontal axis is the gas mass density, and this is the distance. Okay, so far so good, and I think we can call it a day. So we have discussed about solubility trapping. We have modified the model, the aquifer model, and then we have modified the fluid model, and then we run the simulation and visualize the results using, using results, which is very, very, very interesting. And we compare the three cases. And yeah, that's all. In the next video, we will again perform solubility trapping, but we will have different, you know, the diffusion coefficient method. Here, in this case, we have Lingham's method for the Henry's constant, Henry's constant. And on the next video, we will have another method, not from Lingham's method, but Harvey's method. Okay, so that's all. I hope you enjoyed this video. I hope this video is useful. And thank you so much for watching. See you again on the next Eng-Man videos. Thank you.